Alright, so another thing that I want to check was each of these tests should work if uh, right each of these tests should work when we don't create a dynamic map. So let me create a static map. Hash map, create static, null, null, and say 5. Okay, of course we will not be testing the resize functionality, and I would have to update. Okay, so get set. I can add. Okay, resize, right? Okay, so within get set, I can add. This is delete. To add get set function right over here. Okay, so right. Okay, so read count 0, and then we have test get set. Okay, so this should work now. Okay, let's try. Go make, and then okay. So the result RC redefinition of RC. Right, my bad. And result redefinition of result. Okay. Resize, right? Okay. I commented out resize. Right. Great, great, great. Okay, so it should still work fine. Oh, wrong value for map size. 101. Okay. 101. Overwrite. Yeah. So it should be 4. Okay, hold up. Do I overwrite before after getting setting, right? Yeah. So it should be 4. Alright. Great, 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 great. So now I know that it works in starting functionality too. Right, so I am done with this improvement, and then I have to go on to another improvement. Let's check what we can do. What more can we do for improving the hash maps? Okay, so you can use a better default hash. Huh. Okay, so let's find so good non cryptographic hash algorithms. Okay, so several excellent non-cryptographic hash algorithms exist with murmur hash. Okay. So we have murmur hash, city hash, and FNV. Okay, that's murmur hash. Then we have a city hash, another fast hash function. So this family has hash function is known for its speed and good distribution, simplicity and speed. It's available. And okay, spooky hash. Okay, another creation by Bob Jenkins. Okay, so let's try murmur hash. Right. Okay, non-cryptic. The typical example CPU optimized non-cryptic FNV1 and murmur 3. I think I want to implement murmur 3 hash. Okay, algorithms. So we take okay, so this is algorithm. Note in this version algorithmic all arithmetic is performed with unsigned 32-bit integer. In the case of overflow, the result is reduced to modulo. Okay, so we have C1, C2, R1, R2, right? Okay, so we take in the key. M is 5. I don't know M. Okay, and then N. Okay, and hash is seed. Seed which I can give with time, right? Okay, so for each 4 byte chunk of key, 4 byte chunk of key, do. Okay, so we are taking k equals 4 byte. K equals 4 byte. I haven't k, so I'm basically, so k is equals k into c1, and k equals k ROL. What is the ROL? Okay, so we have, okay, a simple C implementation is here. So we have murmur scramble. This is function. We are multiplying it with itself. Okay, murmur 332 scramble. Then I have, we take the seed, read in groups of 4. So I'm copy. Within k, I'm copying key and size of 32. Okay, so I am taking int. Why am I taking a 32 and 8-bit key? Taking a pointer to a key, huh? So seed value is 0. Return h. Okay, h is the hash. Okay. Then we take the key, and then I'm copying this buffer. Size I equals len multiplied by 2. Len. Okay, what is the len? Read in groups of 4. Right, I get it. Key. Key plus equals size of 32-bit int. No, I don't get this. Okay, I don't care about the scramble function. We are copying the value of key into this buffer, and 30 right, len read in groups of 4. So we go len time right shift. Okay, dividing by 2. We're dividing by 2 again and again. So len, I think len can you show me a usage of this function? Okay, this is equivalent of dividing by 2. Okay, len is dividing by 2 and I minus minus. So here is the source of differing results across Indianness. Okay, a swap here has no effects on hash properties though. Okay, reads in group of 4. Okay, 32. This value, read the rest. K0 size 3 len and 3. Okay, okay, a swap is not necessary here because the preceding loop already placed low bytes in the low places according to whatever NDNS we use. Swaps only apply when memory is copied into a chunk. Okay, I don't really understand on any of these functions. So so why is my key supposed to be okay, so write ROL. What is ROL R1? Are we right shifting? ROL R1 and multiply 2. Then see hash XOR RO. Okay, wait. Is it OR left or logical OR? Let me see. Multiplying with C1. Okay, after multiplying with C1, this is the key, right? K is the key. For each 4 byte chunk of key do equals 4 byte chunk, k equals k in c1. Okay, so we c1 is the size of this, huh? And we murmur scramble ROL did chat GPT. Can you explain? Okay, wait. Murmur 3 hash function. Um, hash is a non-cryptic. It is often used in applications like hash tables and Bloom filters when fast lookup are crucial. Okay, so murmur hash and C. I think murmur 3 hash. Okay, so we go here. Yeah, fourth in line. Okay, 32 bit, yes. Const void key. We take a const void key. Okay, length, int length, and then we have a seed, and then we have a value will be provided here. Okay, so we take 1 byte. Okay, so we are going 1 byte at a time. Here, this is a pointer, and right, then n blocks equals, okay, length divided by 4. Okay, so can you, yeah, I want to see an example. Okay, so I have a hash, I have an array, I have a seed value for hash, and then argument. Okay, arg1 seed hash. Okay, memory 3, so I go strlen of arg v1 test.c. Okay, so we have test hash with, okay, so size. Okay, this is the size and this is the seed value, right? Okay, so test hash, we take n bytes. How many bytes is there? Okay, so it is passing in the bytes. Okay, so it takes in the bytes. Okay, so it takes in the bytes, it takes in the seed, it takes in the string, and what it expects. Okay, right. Okay, so it takes in the bytes. How many bytes? So basically the length is the number of bytes, right? And we in example dot c murmur dot c, right? I have this function. So we have basically 32, so 8 n blocks, right? Okay, so blocks equals 32 bit times we have get blocks of I. Okay, I have to say that function was really, murmur 3 function was really easy. Okay, what is this function? rot hash define rotl rot function. What is this function? Behaves as a bitwise left rotation function which shifts the bits of a number to the left and wraps the bits and fall off the left side to the right side. Okay, so bitwise left rotation operation which shifts the number to the left and wraps the bits that fall off the left side to the right side. Okay, so that's what it is. Right, okay. You get blocks P of I. Okay, force inline must be defined. Inline, right, okay. So inline 32. Okay, so murmur hash 3 is finalization mix forces all bits of a hash block to avalanche. Okay. Get block, then we perform write to operation and murmur 3. Okay, so what all headers are included? std int, okay, is rotl function and c, right, okay. So it is defined in limits. Oh. Common implementation of function for an unsigned. Hold up. Function performs the bitwise circular operation. Thus means, while some compilers or libraries must provide intrinsic function like there is no standard ROTL function in C standard library. Therefore, it is typically implemented using bitwise operators. Has this guy implemented? We have inline. Okay, so here he has implemented a right to left 32-bit. Okay, voice function. So one keys that can fill only. Right. Okay. So I think I should really implement it myself. Huh. Okay. So it works, reads in groups of 4. So we have divided it by 4. Right. Length I have divided it by 4. Okay. Scramble. Okay, C implementation. My 32 scramble. Reading groups of 4 is a source of differing results across endianness. A swap here has no effect on hash properties though. Murmur hash. Okay. Need this 32-bit. Okay. So we go mem copy. Size of 32. I would need string for mem copy. Then murmur 32 scramble XOR with this. Then we do this to size I and then 3. Read the rest. So length. Okay, test string. Okay, test 0 0 is this. X value is this. Okay. So let me create a. I will. Okay. Let me just go back and let me create a new. Let's say ex37.1. Murmur 3 hash, right? Okay, so we'll come here. Okay, then I want to create new files. First, okay, source and test. Source and test. And source. Okay. No, yeah, source and test. Okay. And I want to create files. Source main dots. I'll go with murmur 3.h, murmur 3.c, and then I want to create make file, a readme.md license. Alright, so let me bring in. Okay, I have updated um, game development. I have updated the debug file here. Yeah. Okay. So I'll drop in the debug file here. And then I'll copy the test file here. Okay. So we will start. But then I would also have to write my make file. Okay, so source, everything in source, and make file. Okay, so hold up. Let me close this project. Okay, so let's see, flags equals dash g dash I source, and okay, that is all. Then I have the source equals, call this wildcard function with source, let's see, right, this is how you do that. If I'm right, which I have no idea. One with, okay, yeah, right, wildcard, then we pattern substitute. Okay, then object files equal pattern substitute, if I'm correct, right. Right, object pattern substitute, right. So we go pattern substitute. I want to substitute all C files to .o files and from source, right. Substitute from source, and then we will declare a target equals what is the target x test test slash how is target defined here? I just defined main as a target. Okay. Okay. Hold up. Let me take a look at this make file. Okay, so we define, yeah, target is the build, and within test I guess, yeah, test, within test I define the test. Okay, so I've defined test source, and then tests, and substitute test source, and I have different tests. Okay, alright. So target, okay, I'm not building a library, uh, so I'll simply define all compile and link and compile. It depends on objects. Compile depends on objects, and then I can go link is cc then I want object dash go with target equals pen slash uh, target is okay, target is okay, so let me go test source is wildcard dot everything, then we have tests equals pattern substitute dot c files with nothing, right, with nothing, that's how I switch, right, we go with nothing, yeah, and from I want it from test source, so target equals um, tests, nah, this is wrong, okay. So compile, then I have to link, right, I have to link include source, compile link and test, okay, so I'll declare test is it link and tests, okay, so I just have to compile and then I can link with the within the test, right, okay. How does this works? Test, if we go test, then target, so then we go target, so target, then the target I create a shared object, and then target source objects, okay, so build and objects, okay, so target depends on objects, alright, then we have depends on objects and c flags plus equals objects, okay, then it goes to tests, okay, so all the tests are made, okay. C flags plus equals the objects and test is tests, right, and then it run the individual tests, right, so we include the objects in the C flags and okay, we all right, okay, this will automatically build the executables. So I don't have to link because the objects will be linked with the test. So I just have to compile, and then it just tests. Okay, great. Okay, so murmur 3 defined. Murmur 3 H. What just happened? Okay, not defined. Point murmur 3 dot H. Okay, so we want to define murmur 3 H. Okay, and F. Right. So I have to include std_int.h. Right, I have just one function. Okay. T murmur yeah, okay, so I'm here. So we make a key. Okay, so an extra additional thing is to get the key. I have to update the key for each of the length, right? This is dividing it by 4. Length, okay, size the I, length I, then I minus minus. So we are simply a scramble is whatever. I think it's right shift, right, okay. So let me go murmur 332, and I want to give it a key. Okay, it takes in the length of the key, size T length, and a seed. Okay, maybe I don't worry about the seed, right? Okay. 32 32-bit, right? Yeah. So void key okay, so um I feel like I would have I feel like I didn't really need this. Okay, hold up. Okay, but let's do it anyways. Key, and then I would also with key, right? Okay, I'll just work with numbers for now, and size T, length, right? Length, okay. So first of all, we define. Alright, so I should probably write a helper function. Sorry, 3020. Okay, so this is a murmur 32 scramble. Murmur 332 scramble. Okay, I know this is murmur 3, right? So I'll just go murmur 32. I'll go murmur 32 scramble. Right. it takes in a unsigned. Okay, we multiply k with this. Okay, so we have 0 x, we see 9 a to d 5 1. Then we do some bit shifting. Totaling to 32 bits. I think this is the shift operation with the. Okay, this is the shift operation with circular, and it's 7359393. Okay, then we return k. Okay. Okay, so first of all we have a seed. Go hash equals 0 starts with a seed. Okay, and then I have this. Okay, function which I'll also start with 0. Okay, then right, okay, so what this function basically doing is keep the size of 32. Okay, we are copying the key into k, and this is the function, right? Okay, but I don't see I being used anywhere here. Right, read in groups of 4. This is really I don't understand this. Is a source of differing results across India. Swap has no effect on hash properties though. Okay, so we memory copy k key. Okay, this is the key. Huh. Okay, so we are incrementing key. Okay. Okay, so first, so this works on a single byte, right? This works on a single byte, and okay. Key, and we are copying. Okay, I got it. So hash a swap is not necessary here because the preceding loop already places the low bytes and low places according to whatever endianness we use. Swaps only when the memory is copied in a chunk. Okay, then we move by 4 bytes. Okay, okay, if I look at this implementation, right, this is the same function, max. Okay, then we get the seed blocks len by 4, right? 4 byte blocks. V blocks equals to data plus n blocks into 4. Then for I equals n blocks and minus n blocks and I plus plus I is 0. You get block. Right. So P of I. Okay. So I have this function. Okay. Okay, so it takes the block, performs this operation, and then this. Okay. Then tail is blocks plus n. Check if the last 3 bits. Whew. I don't know. Okay. Okay, I haven't wasted enough time, but let me just try it. Okay. Then this is 3. Use a better default hash. Okay. Let me take a look at city hash, right? There was city hash. Okay. Let me go with city hash. Okay, we're releasing 2 hash functions today. 64-bit I want city hash. Faster than murmur. Auto murmur helps me know if the verification is needed and help review design of city hash. Murmur hash, let me know if verification is needed and help review of the design of city hash. City hash has higher throughput and is more complex. Murmur hash has lower latency for very short keys and it's relatively simple. Murmur hash is simple. Okay, I want murmur 1 hash. Just give me a simple hash, right? Murmur 1. Okay. The original murmur hash was created in an attempt. Had been tested thoroughly and was not compatible for 64-bit hashes. Okay, its design would be later built upon murmur hash 2, combining a multiplicative hash similar to with XOR shift. Okay. So produce the same value. Okay, so I have to use murmur hash 2. Murmur hash 2. Okay. Murmur hash. Understanding murmur hash 2. Right. Okay. So it processes. When is this? December. Okay. Hash2. Hash2 developed by Austin Appleby in 2008 is a widely used hash function. Unlike the traditional hash function, which are often used in security context, it was designed with speed and simplicity in mind. This makes it particularly useful as non-security application with the primary concern is fast and reliable hashing. So processes input data. Here's an implementation. Okay, we have length. We take the length of data, then we divide it into blocks. Then we have the seed and C1 and C2. Okay. Then we process each block. So in the block, I go K1 equals struct dot unpack data data of 0. I don't understand this struct. Murmur hash 2. Okay, so let me go and try and understand. Okay, can you explain working of nah, dude, I won't, I cannot do that. Well, murmur hash 2, right? Coin P and a 32-bit seed. Okay, so this is relatively simple. Okay, so mix 4 byte at a time into hash. So I take data and constant side get key. Okay, from the data, I am taking the key, then k is equals to, okay, at a time I'm using len data equals plus. Okay, so I increment data by 4 bytes and decrease length by 4. Switch length. Okay, handle the last few bytes of the input array, and this is it. Murmur 2. A basic refactor of Murmur 2 hashing method. The ANCC compatible and did the same result. Long story short, needed for something. A basic scones build file as all great goes to Appleby. The main project is hosted over at Google Code Investor Page. The suit Appleby hashes. Okay, there we go. Murmur hash 3. Murmur hash 3.cpp. Okay. Okay. Right. Okay, so basically it is that basically what we are indeed doing is, okay, right, so we have this data, okay, right, key, okay, I pass in a key, right, then I pass in data and I create blocks, okay, so Okay. Okay, so I have my key, right? Let's say it has n bytes. Okay, n bytes. Then only want to process. We process 32 bytes at a time. Okay. 32 bytes at a time, right? 32 bytes or not 30, 32 bytes, 32 bits. 4 bytes. 4 bytes at a time. Right, okay. So we define blocks, right? Then I have defined some variables. Okay. Then right to left operation. Okay, here's right to left operation. Right to left 32. X and okay. This include define. Okay, if defined, this is this. See, okay. Big constant x is x. MSVC. So inline if defined this. Okay, if defined MSVC. Where's the end for this? Defined MSVC. Not defined MSVC. Okay, then we get block 32. Okay, and get block. Then this is a function for mixing finalization mix. Force all bits of a hash block to avalanche. What is avalanche? Uh, Avalanche and hashing. Okay. In the context of cryptographic functions, the avalanche effect refers to the desirable property where a small change in the input, example a single bit flip, results in a significant and seemingly unrelated change in the output, the hash value. This effect is crucial for making resistant to various attacks. Okay. Avalanche effect. This article. Okay, so this article is about cryptography. Okay. Cryptography. The avalanche effect is the desirable property of a cryptographic algorithm, typically block ciphers and cryptographic hash functions, wherein if an input is changed slightly, the output changes significantly. In the case of high quality block ciphers, such a small change in the in either the key or the plain text should cause a drastic change in the ciphertext. The actual term was used by although if a block cipher cryptographic hash function does not exhibit the avalanche effect to a significant degree, then it has poor randomization. Okay, and thus a cryptanalyst can make predictions about the input being given only the output. This may be sufficient to partially or completely. Sufficient to partially or completely break the algorithm. Thus, the avalanche effect is a desirable condition from the point of view of the designer of the cryptographic algorithm or device. Failure to incorporate this characteristic leads to hash function being exposed to attacks including collision attacks, length extension. Okay. Constructing a cipher or hash to exhibit a substantial avalanche effect is one of the primary design objectives, and mathematically, the construction takes advantage of the butterfly effect. This is why most block ciphers are product ciphers. What are two or more transformations in a manner? Okay. It is also why hash functions have large data blocks. Both of these features allow small changes to. Okay, so how does it forces it to avalanche? Okay, I can ask for Simple example of avalanche and hash functions. Mm, huh. Okay, demonstrate. Okay, demonstrate the avalanche vector. Okay, hash functions plays a fundamental role in modern cryptography. An important and desirable feature of a good hash function is a non-correlation of the input and the output, a so-called avalanche effect. Non-correlation, which means that a small change in the input results in significant change in the output, making it statistically indistinguishable from random. Okay. The hash function can produce a variety of hashes and return them in multiple formats, making it easy to study hash properties. A hash function demonstrates the avalanche effect if a single flipped bit in the input causes a change, on average, half the bits of the output. Okay, this is an example. Okay, so random. So we are generating 256-bit integers, 10,000. Okay. Define a function that flips a random bit. Okay. Then create a pair of integers that differ by 1 bit. Okay. Flip a random bit. Then check the Hamming distance. Distance is exactly one for each. I don't know what Hamming distance is. Hmm. Okay. So a little change in input should have a drastic change in the output. Okay, so there we go. Hash function is 001, which is this. 001 is this, and 010 is this. Okay. Hash function exhibits good avalanche effect. When a single bit is changed, the hash sum becomes completely different. Okay. So this is what a avalanche effect is. Right. Okay. So this. Then we are taking data. Then we are going through the blocks, right? Get block of I. We get block, so return it just returns value. I know this, Okay, so there will be 0 I for each block. Okay, I equals minus block I plus plus minus of and block. Huh. Okay. So block of minus I x86. Okay, right. Okay, so 4 bytes, process 4 bytes at a time, right? So okay, so in the block, I have a 32-bit block, and within that block, okay, and I am getting a okay. Here data plus n blocks into 4. Okay, I have a 32-bit pointer, data plus 4 blocks. Okay, I get that. We are starting. Okay, we are starting at the rightmost bit, right? And then we are getting a single bit. Okay, then we again go right data, and this is the tail. Okay, so we are looking at single bytes. len. Okay, so tail. Okay, tail is, I think there are some things void out. So 32-bit each one. Okay, so out of course has to be 32-bit. Okay, so we start. Okay, in this function we are starting at the rightmost block. Okay, and we are pointing it out by this. Okay, and then we at the tail we set. Okay, if the len. Okay, so these are number of length. Tail of 0, 1 and 2. Okay, so a single byte is left here, right? Case 3, case 2. Okay, all of the cases will okay, and then we have right. Okay, so that is the magic happening. Okay, so the extra algorithms that I have. Okay, so it has it. So in the book, it was told me that you can use a better default hash. There are tons of them. Okay, so how about I go look at some Bob Jenkins, yeah, hash algorithms. Jenkins hash function. Okay, so this is one at a time. Okay, I think this is the default hash that I use. Behavior is shown on the right. Lookup 2 of the intermittent succession. We have spooky hash released in 128-bit. Lookup 2, it is referred to as my hash in the 1997 journal article. Okay, so the spin model check is a probabilistic error. They study lookup 2 and simple extension of it to produce. Okay, lookup 2 hash function. Lookup 2 hash function. Okay, Jenkins. The term lookup 2 purpose. Where can I find? Okay. What is DJV2? Set lookup 2. Lookup 2 Jenkins function. Okay, it's part of the family of hash function created by Jenkins, which also include one at a time hash and lookup 3. Okay, Jenkins hash enhanced. What is this? Abstract and okay, an enhanced non-cryptic hash function. Spooky hash. Murmur. Okay, Jenkins hash function. Lookup 3 hash functions. Okay, this is the mix. This is the 32-bit. Okay, one at a time, right? Okay, there's a one at a time function. Okay, one at a time. I think then the default hash function that is defined here, default hash. Yeah, I'm using one at a time by Jenkins. Okay. Some options are Murmur 3. What else? Murmur 3. Then look up look up 3 hash function. This is hash little. Then what else do I have? What else function? Hold up. Okay, look up 3. There we go. Alright, so this is hash little. Diamond lookup 3.3 by Bob Jenkins, public domain. This is a function for producing 32-bit hashes. Okay. Double lookup, hash word, hash little, hash big, hash full functions, routines. So I can go to 3 dots C. Okay. So these are functions for producing 32-bit hashes. For hash table lookup, hash word, hash little 2, hash peg, mix, and final are extremely useful functions. Routines to test the hash are included. If self-test is defined, you can use this free for any purpose. It's in the public domain. It has no warranty. You probably want to use hash little. Hash little and hash peg has byte arrays. Hash little is faster than hash peg on little Indian machines. Intel and AMD are little Indian machines. On second thought, you probably want hash little 2, which is identical to hash little except it returns two 32-bit hashes for the price of 1. You could implement hashback 2 if you wanted, but I haven't bothered here. Okay, if you want to find hash say exactly 7 integers, hash of say exactly 7 integers to 1b mix. Okay, then final, then you see as the hash value. If you have a variable length array of 4 byte integers to hash, use hash word. If you have a byte array like a character string, use hash little. If you have several byte arrays or a mix of things, see the comment above hash little. Okay, why this is so big? I read 12 bytes at a time into 3-4 bytes integers and mix those integers. This is fast. You can do a lot more through mixing. 20 to 3 instructions on 3 integers that you can do with 3 instructions. Okay, I think I should stop now. Yep.